Now we can look at the heat equation. Remember that on test 1, you derived the heat equation. And when you did that, you got exactly the PDE, that is the first equation on the page. So now notice, when we talk about the problem of the heat equation, there are actually 3 equations on the handout that all come together to be the problem that we're going to solve. The first line there is the PDE that you derived. The next line is what we call the initial condition. So on your handout, for the top equation, write on your handout PDE by the first equation. And notice that that equation is true for all x in omega and for all t that is greater than t0. Or in other words, t minus t0 is positive. So that's for all space and for all time that PDE holds. The next one is what we call the initial condition, so that's where you write initial condition. Remember in ODE's class, we always had a differential equation, and if it was first order, we had one initial condition. So now notice, in the heat equation, there's one derivative with respect to t, and so we have one extra condition, or one equation, that gives us an initial condition. If we didn't have that, then when we, in theory, do the integral in time, or with respect to t, we would have an arbitrary constant. But since we also have now this initial condition, we would use that to solve for the arbitrary constant. What we will see here is that it's not as simple to just write it in terms of an arbitrary constant and solve for that. Instead, we make sure that up front we have that initial condition, u of xt equals g of x. And we use that from the beginning, so there won't be any arbitrary constant. In fact, there will be one unique solution, and that will depend on that g of x. Notice then the last condition is what we call a boundary condition. And that's where that equation holds, where x is on the boundary of omega, and also for all t greater than t0. Here's a picture to go with that. This is what we are calling omega. It's a shape, or it's what we call the domain, in any dimensional space. In most PDEs classes, instructors like to make these look like a potato. No real reason, they just want to draw a random shape and they all end up looking like potatoes. I made a flat potato. So here's a region, omega, and that's the domain, and so we're going to find the temperature. The unknown u stands for a temperature at all points in this domain at any time t, greater than our initial condition. So there will be some initial temperature at all points in space, that second equation, the initial condition, that g of x will give us the temperature at all points in space, but only at t equals t0. And then after that, it's going to evolve according to the PDE, and the boundary conditions, notice what type of boundary conditions that those are. The name attached to that is Dirichlet. That's because we are prescribing the actual temperature at the boundary, and in fact these are not just Dirichlet, they are homogeneous Dirichlet. And that's because those are the mathematically nicest ones for us to work with. Homogeneous Dirichlet. That's like enforcing the temperature to be 0 everywhere. So if we're dealing with Celsius, then think of the boundary is ice. The boundary is ice. And so there's some initial temperature distribution around the whole body, but then the temperature is being held at 0, like ice. And so then we're looking at how does the temperature change over time? How does the holding ice at the boundary affect the change in temperature over time? So now, right away, in Chapter 6, we are not solving the multi-dimensional problem. This will not be a 2 or a 3D or any higher dimensional problem. When we're just solving the heat equation for the first time, we're doing this 1D. And so our domain Omega is actually just a one-dimensional interval with two boundary points, 0 and L. What's nice about this is we can still, since it's 1D, we can actually graph u. U can be like this y-axis, a function. And we'll see a few of these graphs on the videos in this handout. This function will change over time. That's why I didn't even bother putting a sample one on here. We will see that at a certain time there will be a certain function, and that for every snapshot in time there will be a different function. But notice, if we can enforce those homogeneous Dirichlet boundary conditions, all of these functions will share 2 points in common, and that is right here will be fixed at 0 for all of time, and right here will be fixed at 0 for all of time. So it might do anything else in between, but 0, 0. So this is the problem that we will solve. Notice also, one last thing on the handout, is that the kappa of x, or k of x, is we let it be a function of x for the first 2 times that we wrote it on the handout, but in practically every problem that we solve in this class, kappa will be a constant. And so you see that it came outside the ddx on the handout. So it is rho c u, derivative with respect to t, minus kappa, second derivative with respect to x of u, equals 0. So those are the 3 pieces. The PDE, the initial condition, which is like the boundary of time, but then also the boundary conditions that are on the boundary of space.